Alright, let's continue. Okay, let me open the table of content first. Okay, we are still in chapter 26. Here, concurrency and introduction. Let's take a look at the homework simulation, or maybe to be precise, continuing on the homework simulation. Okay, this one, we already take a look at this question, and this question. Now let's take a look at this one, looping rational log. Okay, let me open my terminal emulator, and what is it? Looping rational log, I guess. Okay, the assembly looping rational log. Assume px has loop count in it. Oh, okay. I think this is the, what is it called? Label, maybe something like that. This is the critical section. We have set resource here, the memory address. Okay, well, I mean, I'm not sure if we consider the register R as set resource. That can cause the race condition, but yeah, I'm still not sure. Okay, and then we move the value from the address 2000 to the register AX, and then we add those value with 1, right? Increment that value, and then move it back from register AX to memory address, and then we do some iteration here. Can px has a loop count in it, but if I remember correctly, the default value is 0, so maybe this one will fail immediately, will false. Basically, this is checking if the value px is 0 or something like that, and we check that with this condition, jump if greater than this result. So maybe jump back to the top, what is it called, label, right? If it is greater than 0. So if it is 0, we are not jump to the top label here. Something like that. I mean, we subtract that first, right? So if the default, what is it called? If the default or initial value of px is 0, the value in px will be -1, and this test will turn false for this condition. So we are not iterate to the top level anymore. But yeah, it depends on the value of px here. Which access asset variable located at address 2000. We'll call this variable value. Okay. Run it with a single thread to confirm your understanding, right? Okay, what is value that is at memory address 2000 throughout the run? Use the C flag to check. Okay, let's do that. Threads intro. Okay, threads intro. Looping there is no log. And then what is it? With one thread here, the testy flag is the thread flag. Where is it? This one. So basically we specify the number of thread being used. The default one is 2 thread here, so we change that to 1 thread, and then we tracking the memory address 2000. This one, list of address to trace. In this case, right, we use the address 2000 to store the content of value variable here, right, something like that. So let's try something like this, I guess, and see if I can answer this correctly. So okay, maybe I should do this instead, right? Okay, the initial value is 0 to AX. I mean, you know what, let's also trace the register using this uppercase R to trace the list of register AX and then PX, I guess. Here we are using AX and PX. I'm kind of curious what happens if we provide the register that didn't exist in the instruction. Okay, we can. Okay. Yeah, there is only 2 AX and PX. I'm not sure if that is expected or not, but looks like we can do that. So I assume the AX here is 0. Okay, not that one. And then okay, this is 0. I think the PX is 0 till this one, until this move instruction probably become -1 after this. There is that 0 again. We are moving the value of 2000, the value from address 2000, I mean, to the register AX, which didn't really change, I guess, at glance at least. And then add 1 to 8. Okay, this one's still 0 because we haven't moved back the, what is it called, the value from register AX to address 2000. Now we move the value from address AX to, register AX to address 2000 here. Okay, this one 1, then finally 1, and then subtract that. Then this one become -1. This, I think still the same. We're basically ignoring this because the condition is not fulfilled, right? It should be greater than 0, the value instead of bx, but we have -1 here. There is that. I think this is 1. Yeah, maybe this is 1. Okay, something like this. This is my first hypothesis, I guess. Let's check. Okay, looks like we are correct here. This one, right? Okay. Alright. It's the same. What is value that is memory address 2000? That is the content at memory address 2000. Well, it is 1 because we only have what is it called? 1 execution, I guess. Not iterate the execution. Okay. Run with multiple iteration or thread. Now that is a problem. Okay. Why does each thread loop 3 times? Okay, let's check. Itu test C, and then we provide the initial value for register bx here. Okay, 3, still this one, and then increase the thread, I guess. Okay, be something like this. Yeah, I want to also track this one, the register AX and BX. Okay, oh, that is a lot. Okay, let me copy that. Okay, maybe not on this one. Let's try this one instead. Okay, I assume this is 0, 0, the initial value, and this is 3 because we provide the initial value here. Bx equal 3, and well, this should be still 3, right? We didn't touch any bx register during this 3 instruction. And then this one is 0, this one is also 0. What is it called? The value in address 2000 coincidentally the same as the value in the register AX, so it looks like there is no change here, but actually there is some change, you could say, that we move the value from register 2000 to, not register, the address 2000 to register AX. So let's say if this what is it called, the value in address 2000 have 69, this one will become 69 too. Maybe something like this, right? But yeah, the value in address 2000 is 0. That's why it is also 0 in register AX, and then we add that value with 1. This is still 0, okay, because we haven't moved back the value from register AX to address 2000. And then during this instruction we move back the what is it called, the value in AX register to the address 2000. This is 1, this is also 1, and then we subtract the the PX register, the value in PX register here, so it becomes 2, and then this is still 1. Okay, I think until this is still 1. Okay, and then this one is 2, still 2, and then we jump to the top label here, this one, so we execute this instruction again, something like that, because the value in register PX is greater than the 0 value here. That's why we jump to the top level again and execute the instruction again. Okay, this is 1, this is 1, maybe this is 2 until before we subtract that value. Okay, and then add again the what is it called, increment the value in AX register by 1, so it becomes 2, and then this one still 1, and then we move that, okay, and then subtract. Alright, okay, wait a minute, subtract that until, okay, yeah, we haven't changed the value in address 2000 and in the address 2000 and register AX during this, what is it called, instruction. This is 1, okay, and then we jump back again because the value in register PX is greater than 0 from this instruction. Jump if greater than the result here. Okay, this is the same again, 1, this is 2, okay, then we add that, become 3 in the register AX, right, and then remove that, something like this. No, I think this is 3, right? This is also 3, I guess. We subtract that 0, we subtract the value in register px, and then test. Okay, we didn't jump because the value in register px is the same or equal as 0. Okay, and this is greater than, so equal is not considered true. Then hard. Okay, maybe to answer this, why does each thread loop 3 times? Well, because we specify the px as 3 and the jump condition only, what is it called? Only become true if the px value is greater than 0. So as we decrement the value in px register, we only iterate 3 times, from 3, 2, and 1. And then when we hit value 0 in the px register, we stop the iteration. We didn't jump back to the previous, to the previous instruction or the label top here. Okay, now switch. I kind of forgot. Do we also save the value in memory address too? Maybe not. If I remember correctly, thread sharing the address space, so we don't need to switch address space, maybe something like that, or switch the page table, I guess. So we only need to save the value in the register from thread 1 here. Thread 0, not thread 1. Okay, this one become 3 again, and then we start out again. Okay, now because the value in register 2000 is different than the value in, not register, the value in address 2000, memory address 2000, this one 3 is different from the value in the register AX. So when we do this instruction, moving the value in address 2000 to register AX, the value will be different. Okay, let me change the value in PX first, because I don't think these 3 instructions have anything to do with PX, so it should be the same. And then because we move the value in address 2000 to register AX, becomes something like this. See, this is different, right? Okay, and then add that, increment that by 1, and then move that back. Now, okay, change this to 4, this to 4. Okay, we subtract that. and then we jump back to the top level again, executing the previous instruction or the critical section here, critical instruction, I guess. Okay, this one the same. Okay, move back. I guess this is the same. Add one. Okay, and then move that. This. Okay. Subtract that. Okay, and then jump again. Okay, this is adding or increment 1 by 1. Then move that back. Okay, this one subtracted, and because what is it called? Because the value in register px equals 0, right? This one, so we didn't jump back to the top level and continue to halt here. Okay, maybe something like this. What is final value? What is final value of variable? Well, my hypothesis is 6, I guess. Let's find out that is correct or not. Okay, looks like it is correct. I mean, in this case, we didn't really have race condition because the thread 0 already finished before we switch to thread 1 here. So the value is correct, I guess. Okay. Hello, Pony Circuit. Welcome. Oh. Did my internet connection drop? Okay. Yeah, at some point my connection internet dropped, I guess. Okay, we are currently learning about operating system by reading this book, Operating System 3 Easy Peasy, and currently on chapter 26, looking at the homework simulation here and trying out this question. Okay, what is the final value of value? It is 6 with this what is it called, with this scenario, I guess. Run with random interrupt interval. Okay, do we need to provide this, the interrupt, what is it called, direction maybe? I'm not sure. Okay, set 0. This is the random flag for interrupt. Okay, with different seed. Okay, can you tell by looking at the thread interleaving what the final value of value will be? Does the timing of the interrupt matters? Where can it safely occur? Where not? In other words, where is the critical section exactly? Okay, in case anyone new, the default interrupt, what is it called? Frequency, right? This one is 50 instruction. So we have interrupt every 50 instruction. And what I mean by instruction is this one. This is the first instruction. Add is the second instruction. And then the next one. So this is the instruction. So if we have this one, right? The interrupt frequency 50, it means that we will have interrupt, what is it called? We will have interruption every 50 instruction. Every 50 instruction, this kind of instruction. Something like that. I guess if we didn't provide this, the random will be maybe 1 instruction to 50 instruction between those range. So we narrowed that. Instead of 50 instruction, we got 4 instruction before it interrupts. Let me show you what is it called? What happened without the random interrupt interval or frequency. This is with the interrupt frequency 4. And it is consistent, interrupting every 4, what is it called? Every 4 instruction. Yeah, it is consistent until the thread finish, something like that, or the program finish. For example, this one, the thread 0 already finished at 3 instruction. So we switch to thread 1, and thread 1 also finish. Not finished. Thread 1 continuing only 1 instruction before interrupt, and then continue again. So we can think of interrupt frequency like, what is it called? The interruption every specific instruction, and that does not matter on which thread the instruction is. So it is the total instruction, what is it called? In each thread, I guess. In this case, we have 4 instruction before the interrupt, 3 instruction on thread 0, and 1 instruction on thread 1, something like that. Okay, and then let's try to add random interrupt here, which mean it's not necessarily gonna be 4 instruction every time the interrupt happen. Sometimes it is 4 sometimes it is 2 instruction before the interrupt. So it is the interval, what is it called? Maybe between the specified interrupt frequency. This is what it means by random interrupt. Okay. Can you tell by looking at the thread interleaving what the final value of value will be? Final value of value will be. Does the timing of the interrupt matters? Where can it safely occur? Okay, let's try answering this by looking. Only looking, okay. Wait a minute. Px is 3, okay. Well, I need to, what is it called? At least take note, I guess. Okay. This one is 1 subtracted, and then this one is 2 now. Okay. This one test again. Okay. Going to the top again. Okay. This one is, what is it called? The value in 2000 is, in address 2000 is I guess 3 now. And then this one, this might be the problem. Okay, it is still 3 from this one. I mean, we already add the value in the register AX on thread 1, but we haven't moved back to the address 2000. So the value in address 2000 here should still be 3 instead of 4. Okay, subtract that. Move that to register AX. Okay. And then this one. Okay. This one means that we still have 3 in the address 2000. So basically we are replacing the value in the address 2000 from thread 0. Replacing address 2000 thread 0 thread 1, maybe something like this. That is the problem there, I guess. And in the thread 1 here, the AX also have 3 value. So even though we are replacing the value in address 2000, we are replacing that with the same value 3, and then subtracted. And then we add that again. Now it become 4. We are replacing again. Now the situation is reverse, right? Now that one replacing value, I guess, in thread 1, or maybe not in, but from that one. Okay, and then we test again. Move back. Okay, we have 4 now. Okay, this is subtracting. Okay, 4, and then This one should be 5. Okay. Now we have 5. Value equal 5 instead of 6 like the previous one. Right, this one. Okay. And then okay, does the timing of the interrupt matter? In this case, yes. Because again, if the interrupt, what is it called? If the interrupt here, oh, not that one. If the interrupt here, right, happen after this instruction, which means we already move the value in register AX back to the address 2000, we can resume the, what is it called? Resume the operation on the thread 0 safely. So instead of getting value 5, because we are replacing the previous value that we already calculate in thread, what is it called? In thread 0, we can continue to the next value. Maybe something like that. So does the timing of the interrupt matter? Yes. Where can it safely occur? When we already move back the value from the register to the memory address or the shared resource, I guess, something like that. Okay. Now let me try checking that with calculate here. See, the value become 5. Value of value variable instead of 6. And now let's try random seed. The default is 0, right? That's why I didn't specify that. Okay. Now this is interesting. Yeah, this is another scenario, I guess. So basically, before thread 1 can do anything, I mean thread 0 here, thread 0 can do anything with the value within address 2000. We have interrupt, and then we continue that in thread 1. But the thing is that, okay, the value in register AX in thread 0 is out of date. It is not the up-to-date value of address 2000, right? But we still add that, and then we are replacing this one. We are replacing the value, what is it called? We are replacing the value that already been calculated in thread 1 here. So instead of increment the value in address 2000, we are basically have the same value here. from thread 0 and thread 1. So that is the problem. And I think this is gonna be okay. This is 1, this is also 1. Okay. Alright. This is 2, right? This is also 2. Okay. Oh, this is 3. Finally, after we add or increment the value in AX, we move back the value to address 2000. Add 1. Okay. Wait, let me check. 1, 1. And then this is 2, right? This is also 2. Yes, the thread keep replacing each other result instead of increment the result. Then this is 3. Okay. This is also 3, I assume. Out. Okay. The next one I think is 3 with seed 1. Random seed 1. Okay. Yeah, it is 3. So the point or the problem is this. Its operation on thread 0 or thread 1 keep replacing the value in address 2000. So instead of increment the value, we just stagnant with the same value over and over again. Something like that. Where can it safely occur? Well, if I understand correctly, as long as we move back the value this one, after we move back the value from register to the memory address or shared value. So this might be the important one. As long as interrupt happen after this instruction, it doesn't really matter, I guess. Maybe something like that. We can take a look at this one. The interrupt every 4 instruction. Let's check that out. Okay, looks like there is some problem here. Okay, yeah, this one and this one. So here, maybe not 4 but 3, right? So we make sure that we have interrupt after we move this one, after we move the value from the register to the address 2000. So we make sure that we have the up-to-date value in address 2000 before we increment that like this. Yeah, maybe something like that. where not, well, anywhere, I guess. The only safe one is after we do something with the value, we save that result back. That is the safe one. Other than that, I don't think it is safe. We will get different value here, right? In other words, where is the critical section exactly? The critical section, I assume, well, from the assembly file, it is this tree, right? So maybe this tree is the critical section, because we need to have up-to-date value in register 2000 before doing any operation, and then move it back to the address 2000. Maybe something like that. Okay. Oh. Yeah, my internet connection is not stable. Okay. Try to see the assembly. Quite a span. Yeah, I mean, that's what interesting, you know. We keep changing the programming language here. From the Python to C and then now assembly. I mean, this is, I guess, the subset of assembly, not really the full x86 instruction or instruction set architecture, ISA. Okay, this one from the README. The assembly code that is run is based on x86 but somewhat simplified. Right. There are 4 general purpose register and a program counter. Small set of instructions which will be enough for our purpose. Right, it is based on x86 assembly, but only a few of the instruction, a small set of instruction, something like that. And we have this register, this 4 general purpose register, and I guess this is 16-bit register, maybe something like that. I mean, I remember if it is, what is it called? If it is 32-bit, we have this E at the front, extended or something like that, EPX. And if we have 64-bit, we have R. I'm not sure what R stands for, but yeah, that is the difference there. Okay, now examine fixed interrupt interval. Well, you know what, let's continue this on the next session. So that's it for now. Thank you for watching and see you next time. Bye bye.